this video where we're going to discuss exponential functions. An exponential function is in the form of f of x equals a to the x, and we call a the base. And it's important to remember that a has to be positive and it can't equal 1. So here we have an exponential function, and I know this because it's in the form of a to the x. In this case, we have a negative x, okay, which is just a reflection. And this would be a reflection over the y-axis. So technically, it would take the graph of 2 to the x, and it would reflect it over the y-axis. So we would multiply the x's by -1. But we can also just simply plug in values for x and substitute them in. So let's say we plug in -2, -1, 0, 1, and 2. Okay, so if I plug in -2 for x, really what I have there is 2 to the second, which we know is 4. Okay, 2 to the -1 is really just 2 to the first, which is 2. And then any number to the 0 power is 1. And then we have 2 to the negative first, which is really 1 over 2 to the first, or 1/2. And 2 to the negative second is really 1 over 2 to the second, or 1/4. So now when I graph this, it's going to look something like this. And exponential functions take on this form. So it's going to get really close to the x-axis, but it won't pass through. In the last lesson, we talked about that line being called the asymptote. So here we have a horizontal asymptote where the graph will get closer and closer to y equals 0, but it actually will never equal 0, right? So if I was to plug in a 3 here for x, you would get 1/8. A 4 would give you 1/16. A 5 would give you 1 over 32, and so on. So it's going to get closer and closer to 0, but never actually reach 0. So the important thing is here, since it's not actually reaching 0, again, we have a horizontal asymptote there, and that's y equals 0. You can try the next problem on your own. Again, you can always graph 2 to the x, which is the parent function, and then you can try transforming it. So think about what the negative would do to the graph, and then think about what the +3 would do to the graph. Or you can plug in values for x and then solve it that way. Now, an exponential equation is going to be an equation with a variable that's an exponent. So an example could be if you had 2 to the 3x power equals 7, or even 2 to the 7th. Okay, that could be an exponential equation, right? You have an equation, you have an equals, and here you have an equation with the variable as an exponent. Okay, and our job would be to figure out what value of x would make the left and right expressions equal. So the way we solve it is if a is greater than 0, okay, remember that we get that a from the form of an exponential equation, a to the x. So if a is positive, and if it doesn't equal 1, and a to the x equals a to the y, then that tells me that x has to equal y. So in other words, if I had, let's say, 2 to the x equals 8, Well, if you notice, both of those bases are the same here, but here one base is a 2, the other's an 8. I can turn an 8 into a base 2 by just making it 2 to the third. So if the bases are the same, that tells me the exponents have to be the same. So x would just equal 3. And that's all this is saying. Here's another example. So here we have an exponential equation. I've got a variable as an exponent. 9 to the x equals 27. Right now my base is 9 and my other base is 27. I can change them into the same base. I can change a 9 into a 3 squared, and I can change a 27 into a 3 to the third. Now my bases are the same. They're both 3. So that tells me my exponents have to be the same. So 2x would have to equal 3. And if I solve for x, I get 3 halves. And that makes sense. So if you want to check it, 9 to the 3 halves power, remember, is just the square root of 9 to the third, if you rewrite it. And the square root of 9 is 3, and 3 to the third is 27. So that works. Let's try another one together. We've got 32 to the 2x minus 1 equals 128 to the x plus 3. So here my bases are not the same, but both 32 and 128 can be turned into a base 2. I know 2 to the 5th is 32. And I know for 128, it's 2 to the 7th. Now both of my bases are 2. That means that my exponents are equal. But here we want to be careful. It's 5 times the quantity 2x minus 1 equals 7 times the quantity x plus 3. And then we'll solve that. And I'm going to subtract 7x from both sides and add the 2. So x would equal 7/3. You can pause the video at this point and try letter A of the next problem. Let's talk about a famous base. It's called E. It's also known as Euler's number. And it's named after a mathematician, Leonhard Euler. And basically what he discovered was as m becomes larger in this expression, 1 plus 1 over m to the n power, the y value becomes closer to an irrational number which we call E. And E is approximately equal to 2.718281828, etc. It's irrational. It's like the number pi, so it's non-terminating, non-repeating. And I can show you here, if you go to Desmos, if we were to type in here 1 plus, and then I've got 1 divided by, we'll use m, and then it's to the m power. Okay, and we're going to make m a slider, and we're actually going to change this from 0 to, let's go to 10,000. So if I was to plug in from anywhere from 0 up to 10,000 for m, okay, and we'll count by tens, what that would look like. So pay attention to the number that it's giving you in the top line there. Right now it says equals 1, because if I was to plug in 0, we know that any non-zero number to the 0 power is 1. But now if m changes each time, notice that that value is staying pretty close to 2.718, etc. So that's Euler's number. It's the letter E, and it is an irrational, non-terminating, non-repeating decimal. Okay, and e is a base that we use in exponential equations and functions. So here we've got e to the x squared plus 5x plus 6 equals 1. And I'll let you try this on your own, but I'll get you started on it. So right now you have to think about, in order to solve this, you need to make the bases the same. And this base is e, and that's 1. So can I turn a 1 into a base e? You can. So you would have e to the x squared plus 5x plus 6 equals e to the 0, right? Anything to the 0 power is 1. And now, since my exponents are the same, or since my bases are the same, I can set the exponents equal to each other and then solve for x. Let's look at an application problem, which you can pause the video and read to yourselves. Biologists studying salmon have found that the oxygen consumption of yearling salmon in appropriate units increases exponentially with the speed of swimming according to the function defined by f of x equals 100 e to the 0.6x, where x is the speed in feet per second. Find the following. So we want to find the oxygen consumption when the fish are still. So when the fish are still, their speed would be 0. So all I'm going to do, and we know that speed is x, right? I'm basically finding f of 0. So we have 100 e to the 0.6 times 0. And that would equal 100 e to the 0, and we know that e to the 0 is just 1. So my answer is just 100 units. So when the fish are still, the oxygen consumption is 100 units. So in the next question, we need to find the oxygen consumption at a speed of 2 feet per second. So you guessed it, we're going to plug in 2 for x. We're going to have 100 e to the 0.6 times 2. So we would have 100 e to the 1.2. And we're just going to type that into the calculator. So if I type in 100 and then e, and then we need a power, so it's to the 1.2, you get 332, and then some change. So it's about 332 units. So when the fish are moving at a speed of 2 feet per second, they use up about 332 units of oxygen. And that's it for that lesson. If you have any questions, please feel free to reach out.